will be recorded. So this is the schedule for this evening webinar. So first, I'm going to provide some introduction and public relations information, as well as Dr. Olivia will speak on a day in the life of an astrochemist, then which will be followed by a Q&A session, and then we'll end with a poll, a brief poll and concluding remarks. So what is the Younger Chemist Committee? The Younger Division is Younger Leaders Transforming the World Through Chemistry, and the mission is advocate for, develop, and support rising chemists to positively impact their careers, the ACS, and the future of chemistry. And that's one of the reasons why we hosted this webinar tonight, to provide, to advocate and support younger chemists. So there is an upcoming webinar which will be hosted by ACS Webinars tomorrow from 2 to 3 p.m. Eastern Time. And this is just this webinar is free with ACS membership. And this is just an opportunity to meet the 2024 ACS President-elect candidates, which is Dorothy and Florian. And this is just an opportunity to get to know what their goals are, and also to ask questions about their initiative as the President-elect for 2024. I mean, I will include the registration link in the chat after this brief presentation. There's also another opportunity that's provided by the ACS Younger Chemist Committee, which is called the Younger Chemist Leadership Institute Award. And this award is, for younger chemists, anyone 40 and under. International applicants are welcome to apply. And this award basically provides the opportunities for younger chemists to attend the Leadership Institute, which will be hosted in January 2024. The deadline is coming up on October 15th. And so definitely this is just an opportunity to connect with ACS governance, connect with ACS members, and also participate in leadership courses. And even there's also a lot of opportunities to network as well. So it's a really great program, especially if you're interested in wanting to develop leadership skills as a younger chemist. There's another webinar coming up on October 5th, which is a webinar more specifically on networking. And Dr. Matt Granbois from DuPont, he will share actionable tips and tricks for growing your network, especially for coworkers inside the workplace. So if you're interested in learning more of how to develop networking skills, this is certainly a good webinar to attend. And there's also the Younger Chemists local section leadership series event coming up on October 25th. This is more, if you're involved in a local section Younger Chemist Committee, or if you're interested in wanting to learn more about the local section Younger Chemist Committee, this is a really good networking event to network, connect with fellow younger chemists in your local section, or even maybe outside of your local section. And also this series will be hosted virtually. And also there's, great opportunities to connect and brainstorm ideas, challenges that your local section may have or other local section may have. So it's just a good opportunity to bring local section leaders and volunteers together for networking. The Younger Chemist Committee as a travel award, the deadline is November 15th. It's called the CIBA YCC Travel Award. And this award provides an opportunity for younger chemists, 40 and under, someone who's either a postdoc or within the first 7 years of their professional career. This award provides the opportunity for them to, it supports them to be able to attend one of the ACS national meeting or one of the regional meetings. And the award is up to $1,000 for this travel award. So definitely, if you feel like you met the criteria, we definitely encourage you to attend. And just to let you know, there's going to be a Q&A session right after the day in a life talk. So please feel free to ask questions. You can use the chat if you want, and also, even after the presentation, you can even unmute yourself and ask questions as well. So now I'd like to introduce our speaker for today, Dr. Olivia Harper. Dr. Olivia Harper Wilkins is an astrochemist and artist currently doing research at the NASA Goddard Space Flight Center as a NASA postdoctoral program fellow. At NASA, Olivia primarily conducts experiments to explore the connection between cosmic ice, chemistry, and gas phase molecules that are observed with radio telescopes resembling giant satellite dishes. She also uses telescopes, specifically the Atacama Large Millimeter Submillimeter Array, to study the chemical distribution of so-called complex organics, such as methanol, in interstellar space. Olivia earned her bachelor's degree in chemistry, as well as a bachelor's degree in mathematics from Dickinson College in 2015. Afterwards, she spent a year in Germany as a Fulbright research fellow in the Cologne Laboratory Astrophysics Group. In Germany, she and her husband welcomed their son Gunther. Olivia then moved her family to California to pursue a PhD in chemistry while doing observationally astrochemistry research at the California Institute of Technology before coming back to NASA to get back into the lab. Olivia wrote and illustrated Astrochemistry 2021 for the ACS in Focus series and was named a 2020 CAS Future Leader. She is involved in the ACS as an associate member of the National Younger Chemists Committee, member at large of the Maryland local section, and chair of the newly reinstated Maryland Younger Chemists Committee. You can read more about her love of radio astronomy and involvement in ACS in the July 17, 2023 issue of CNEN. Outside of chemistry, Olivia enjoys coffee, traveling, and Minecraft with her husband and son. So welcome, Dr. Olivia.
Great. Thank you so much, Julian, for the invitation. And thank you all for being here. I'm excited to talk to you about astrochemistry. Julian, can you just confirm that you can see my screen?
Oh, yes.
Sweet. Okay, cool. So I'm really excited to talk to you about astrochemistry and my path into astrochemistry, and also a little bit about what I'm doing currently at NASA. So this was already mentioned a little bit in the introduction, but I wasn't really interested necessarily in being an astronomer when I grew up. But when I was 7 years old, I saw this giant satellite dish looking thing in the mountains of West Virginia when I was on vacation with my family. And I remember scribbling this satellite dish in my notebook. It was just huge. It really was imprinted on my mind. And when I was 18, I went back to West Virginia with my family to see what this satellite dish belonged to. And what we found was that it was actually this radio telescope, the Green Bank Telescope, or GBT, which isn't a satellite dish at all. It's a telescope that explores the invisible universe, which I think is just a really cool concept, to think that we can use use tools like this to look at radio waves from space. But the science part is cool, but I was really, really excited about the instrument itself, because it's the largest movable object on land. So the only thing that's bigger than this would be like an aircraft carrier, which is, in the ocean. But it's taller than the Statue of Liberty. It weighs 17 million pounds, and you can still move it. The dish size is more than 2 acres, so you could fit 2 American football fields on the dish without the end zones. So it's really this cool piece of equipment, and I was really excited about it. I had been excited about science generally growing up, and I knew I wanted to be a scientist when I got older, but I didn't know what I wanted to be. And when I learned about the GBT, I wasn't thinking about being an astronomer or doing any kind of space science. But instead, I decided to pursue chemistry because chemistry is the central science. I'm sure we've all heard that in our high school classes, or there's an ACS journal called Central Science. So I think we're all convinced that chemistry is the central science. So I went to Dickinson College, which is near where I grew up in Pennsylvania. I also studied math because math is fun. But when I was studying chemistry, I got really into chemical ecology. And that's because in my general chemistry class, the lab portion was cross-listed with a biology class. And the first lab we ever did was we went to the college farm and we collected cucumber beetles and cucumber plants and did some experiments to learn about the different chemicals. And I also liked this class because I got to do art. So this is a picture from my lab notebook in that first class. And when I had been in high school, I became convinced that art wasn't really worth pursuing. Even if you did really well in an art class, art at my high school was weighted such that it would lower your GPA. Even if you got an A, compared to getting a lower grade in an AP or honors class for math or science, it would lower your GPA. So I didn't think that art was valuable. But in this class, I saw that there's a value in art, not just for enjoyment and entertainment, but also in the sciences. So that was something that was really exciting to me. So I was really turned on to chemical ecology, but I couldn't get this idea of exploring the invisible universe out of my mind. I still kept thinking about these radio telescopes like the GBT. So I applied to do summer research at Green Bank Observatory. I got rejected the first time around, but I tried again and somehow convinced the observatory to let me come on as a summer student, as someone who had never taken an astronomy class, had no astronomy research background, but I had laboratory skills and I had data analysis skills, attention to detail. And so those skills, mostly from my chemistry classes, were enough to convince them to take me on. So I worked in Green Bank. Here's a picture of me on top of the GBT, not while I was a summer student. This is actually from graduate school. But I was really excited to be there. And near the end of that summer in 2013, before my junior year, there was a summer camp where they had some guest speakers come in and someone came to talk about astrochemistry. And I'd never heard of the word astrochemistry before this point. So I went to the guest lecture. I sat in the back behind all the high school students, and I was just blown away by this idea that I could use my passion that was growing into an obsession with radio telescopes and combine that with my background in chemistry. So I decided in that moment that I was going to be an astrochemist because that's what I was really excited about. At the time, I was also thinking about studying abroad at my college. A lot of people, I think something like 75% of students study abroad in their junior year. I had no interest in studying abroad, but I did have an interest in visiting some other really big telescopes. So even though I didn't want to study abroad, naturally, I went abroad and studied at the University of East Anglia in England. And I had a pretty rough time. I was lonely. I had a hard time understanding what people were saying through their very heavy accents. And I just wasn't prepared for that. So that was some real culture shock. But what I really did enjoy was getting to go visit this telescope, which is near Manchester on the other side of England. This is the Lovell telescope. It's the third largest fully steerable single dish telescope in the world. So I went abroad just to go visit this telescope, and then also one in Germany, and I'll show a picture of that a little bit later. But because I didn't have a good time in England, I decided that I wasn't really interested in going back abroad, especially back to Europe ever again at that point. But as we'll see, chasing telescopes has guided my path for much of my career since then. So when I did get back to the US before my senior year, I was a summer student at Harvard University working in the Center for Astrophysics. Again, I got rejected from this opportunity. I had applied for their astrophysics program, and fortunately, there was a professor who I had been in contact with before applying who said that they had money for me. And if I got rejected from the program, they had money to bring me on. And I'm really, really thankful for that and glad that I had reached out to this professor because I had a great summer doing astrochemistry research for the first time. So, networking is important. We have some networking events through YCC coming up and webinars with tips for how to network. So I definitely recommend going to those. But while I was at Harvard, this is the telescope I was using. This is the IRAM 30-meter telescope. It's a radio telescope in Spain. And I was looking at data from this telescope. I was looking at rotational spectra of molecules. So these are chemical fingerprints of molecules from space. And I was cross-referencing my spectra, those chemical fingerprints, with a database called the Cologne Database for Molecular Spectroscopy, or CDMS. And I felt very much like a forensic scientist, where I was, looking at fingerprints and cross-referencing those fingerprints with an FBI database. It was kind of a similar concept. But I really enjoyed this work, but I wanted to know what it was like to work in the lab doing astrochemistry and to work on the other side of that CDMS database. So after I graduated from Dickinson, I went abroad again. As I mentioned, I was never going to go abroad again, but I changed my mind, I guess, in part because of this telescope, the Effelsberg Radio Telescope, which is the second largest fully steerable single dish telescope in the world, radio telescope in the world. I was working about an hour and a half from this telescope by train at the University of Cologne. That's where CDMS is housed, and I was doing laboratory astrophysics. Another cool thing that happened while I was in Germany was that I got to do what every astronomer at least secretly wants to do during their career. I discovered new life in Gunther, my son. So I had a baby in Germany, and that was a really cool experience that I wasn't expecting to have going into it. But my husband and I brought home Goonie, and then we moved to California for grad school, where I did my PhD at Caltech. And there I had the idea that I was going to do observational work, as while I was in Germany, I missed that observational work. But I also wanted to do lab work. Unfortunately, I ran out of time to do lab work. I had a lot of telescope data, which is always a good problem to have. So my laboratory looked something more like this. This is the Great Orion Nebula, and I was studying star formation and the chemistry alongside star formation in this nebula using ALMA, or the Atacama Large Millimeter Submillimeter Array. So this is another radio telescope, but instead of being a single dish radio telescope, you have a bunch of individual antennas that work together as one large radio telescope with lots of holes in it. So it's a way to make a much larger telescope, have higher spatial resolution, get better pictures of the chemistry in star forming regions, but you don't have to worry about the high cost of a single dish telescope. I think ALMA can be as big as 16 kilometers across. So that would be too huge and too expensive to be structurally sound. And while I was in grad school, I continued doing some artwork. So you can see it behind my head, but also here's another picture. I was really excited to have one of my submissions for cover art for one of my journal articles selected for the Journal of Physical Chemistry A. So this is a picture of it, and that's about work that I was doing using ALMA to study methanol in Orion. So again, I'm doing observations, and I'm missing the lab. I just keep going back and forth in terms of what I want to do. So I'm missing the lab, and I decide I definitely want to do some lab work in a postdoc. So I applied to and was accepted to the NASA postdoctoral program, or NPP, at NASA Goddard Space Flight Center. So in the top left corner, you can see Building 34 on Goddard's campus. This is where my lab is. And then you can also see a picture of me on my first day in front of the Goddard sign. We have a much nicer looking sign now, but I haven't gotten around to taking a new picture with it. So I'll talk more about my work at Goddard in a moment, but I want to pause and just share some lessons that I learned along the way. The first thing I learned was that your career isn't defined by your major. And what I mean by that is you aren't limited to doing just chemistry or just whatever you're studying. You're learning skills that can be applied to a whole wide range of things. So if you're creative, you can think of ways to apply your majors to whatever interests you. And it might it might turn out that whatever you want to do eventually, you don't even know it exists yet, and there might not be a major for that. I hope you don't feel too locked in, especially if any of you are undergraduates who are determining a major soon or questioning your choices. Whatever you're doing isn't defined by your major. Another thing that I learned is that you can be a scientist and whatever else you want to be. In my case, it's an artist. So a lot of scientists and have different hobbies, and you can keep up with those hobbies, even if they seem like they don't really belong in your science. And sometimes those hobbies might even be able to become professional activities that you do. So if you want to be a professional scientist and a professional whatever else, you can totally do that. There's no rule that says that you can't. Next, connecting with people is critical. I mean, I think all of us have heard network, 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 and I'm going to say it again. Connecting with people really is critical. In my case, for example, when I was working at Harvard, if I hadn't reached out to that professor and made a connection with them, I wouldn't have been able to work at Harvard because I got rejected from the formal program. So sometimes these connections can kind of open up back doors to opportunities that you might have otherwise missed out on. But it's just important to meet other people in your field, to collaborate, to have future colleagues, but also to benefit your career and your advancement as well. And then the final thing that I'll be focusing on is that astrochemistry really is out of this world. I love the field that I'm in. I think it's a really fun, interesting area of science, and I'm really excited to get to share that with you today. So the first thing that I'll talk about is a little bit of the history of astrochemistry and the types of questions that astrochemists study, and then I'll give you some examples from my work at NASA Goddard of what an astrochemist can do. So astrochemistry is the study of molecules in space. We're interested in what molecules are out there, where they are, how they formed, what they're doing. And this field really started at Mount Wilson Observatory, which I illustrated on the right, in 1937 when the first interstellar molecule, CH, was observed. And something that was really cool about going to Caltech, which I didn't realize until a few years into my graduate program, was that Caltech is just south of the San Gabriel Mountains, where Mount Wilson Observatory is, and you can actually see the telescope dome from campus. So it was really cool when I realized that I could see where astrochemistry began from campus. That was a really inspiring moment. But since 1937, more than 300 interstellar and circumstellar molecules have been detected. And that might not sound like a lot. We have hundreds of thousands of molecules on Earth. But when you think about the fact that probably most of us on this call believed that space was empty or a pure vacuum at some point in our lives, and some of us might still think that, and that's a common misconception that I certainly had. But there's actually lots of chemistry that happens in interstellar space, but the conditions are extreme compared to Earth standards. So it really is a wonder that you could have any chemistry that's happening in space. So to understand this chemistry, to understand what's happening with these more than 300 molecules is really an astronomical puzzle. And it's made up of three types of pieces. You have an observational piece, a laboratory astrophysics piece, and then theory and computation. So I have experience in observational and laboratory. I'll be focusing on the laboratory today. But just to briefly go over all of these, Observational astronomy can show us the molecular distribution, so where molecules are in relation to different environments in space. But observations can also give us a way to probe the physical parameters. We can use molecules as thermometers or whatever other types of tools to learn about temperature and density in astrophysical environments. Laboratory astrophysics can look like what I was doing in Cologne, Germany, where I was doing experiments to populate spectroscopy databases that would later be used by astronomers. But we can also try to fill in the gaps in our understanding of chemical networks by running experiments to try to piece together reaction networks, but also just to study things like reaction rates and kinetics. And then finally, the area that I'm least familiar with is theory and computation. So that might look like modeling how chemistry changes over time. So the chemistry that's happening in interstellar space takes place over millions of years. And even though a PhD sometimes feels like it takes millions of years, you can't just sit there and watch the chemistry from start to finish. Instead, we have to use computational models to see what's happening in interstellar space. And then we can also use theory and computation to help predict spectral lines. So if in our laboratory astrophysics work, we have too many lines to characterize with experiments, we can fill in the gaps with computations. We can also use theory and computations to predict what the molecular signatures of molecules that are unstable on Earth might look like. So for molecules that might be too difficult to simulate using experiments. So there are lots of space environments in which we can study chemistry, but it really begins in molecular clouds. So I'm just going to give you a crash course on what molecular clouds are, because these are our interstellar laboratories where chemistry begins. The chemistry that is on Earth, that's surrounding us, that makes up our bodies, all started in a molecular cloud in an interstellar laboratory. If I throw up this phase diagram where we have temperature on the x-axis and pressure on the y-axis, a generic phase diagram looks like this, where you have solids, liquid, and gas. In interstellar space, you can cover a range of temperatures. You can go up to 1,000,000 Kelvin in certain environments, especially close to the galactic center. And then you have lots of other cold material, but all of it is at low pressure, low densities. So you're always going to be in the solid and gas phase when we're talking about interstellar space. You're never going to have liquids in the interstellar space or the ISM. And it's only a small portion of the ISM that we're really interested in as astrochemists. We're only interested in where the molecules are, which is in these molecular clouds, and they constitute only 1% of the volume of the ISM. By volume, they aren't all that prevalent, but they also take up 50% of the mass of the ISM. So in terms of the amount of matter, it really is quite a lot. It's just squeezed into small volumes. And these clouds are quite cold. They have temperatures on the order of 10 to 30 Kelvin. And those temperatures get warmer as you start to form stars. But 10 Kelvin, the quick conversion that's negative 442 degrees Fahrenheit. So that's very, very cold. So the fact that chemistry that can happen at negative 440 degrees Fahrenheit is just amazing. And when we think of stars, we think of their fiery balls of gas. They're very hot. So the fact that stars come out of this very cold gas is quite remarkable to me. We're also looking at low densities. So the chemistry that's happening in molecular clouds is happening where the densities are between 100 and about 10 million molecules per cubic centimeter. To put that into perspective, the air that you're breathing right now has 10 to the 19 molecules per cubic centimeter. So the threshold for dense in interstellar space is 10 to the 17 times less dense than the air that you're breathing. So again, how can chemistry happen in these environments where there's basically nothing? Air feels like nothing. The air we're breathing feels like nothing. And we're trying to understand chemistry that's happening in an area where it's 10 to the 17 times less dense than that. That's just, again, amazing to me. So here's an illustration of a molecular cloud. This is Taurus molecular cloud. And I'm showing this because it shows that molecular clouds can have different structures. So you have some more diffuse materials around the edges, but then you have these filaments and these cores. And these are the denser parts of the cloud. And cores in particular are where you're going to have stars forming eventually. And these clouds materialize, form stars, and dissipate on timescales of several millions of years. So that's, again, why we need computations to study what the chemistry looks like over time, because we can't observe from start to finish. Instead, when we're observing, we have to get snapshots of different environments at different stages of star formation and try to pull together a piece of what star formation and the chemistry alongside star formation looks like. So in these molecular clouds, most of what we're looking at is gas. So 99% of the mass is in gas, and then the rest is dust. And even though we have only a small amount of the mass being dust, this dust is really, really important. So this dust catalyzes the formation of molecules in the clouds. So since the densities are so low, we rely on dust grains that are they're as fine as talcum powder. So they're very small grains. And we rely on those to hold atoms in place so that and molecules in place so that chemistry can happen. So an example of this is if we form methanol, which in my field is a complex organic. So if I say complex organic throughout this talk, complex means 6 or more atoms. So any of the starting materials that you used in organic chemistry, I think that they're complex. And I'm trying to understand how those things formed, which when I was taking organic chemistry, I never thought much about methanol or methyl formate. Those were used to make actual complex things. But astrochemists are trying to figure out how those things formed in space. So if we start off with something like CO, someone's touching their screen, so if you could please stop because you're putting arrows all over the place. But if we have CO or carbon monoxide, it can be frozen out onto these dust grains, and then you can form methanol by successively adding hydrogen over and over again. So these hydrogen atoms come in about 1 per day. They land on the grain, they hop around until they find a place where they can form a chemical bond. You form methanol. And then by some mechanism, that methanol comes off the dust. It can freely rotate once it's in the gas. And as it's freely rotating, it's emitting energy at radio wavelengths that can be picked up by a radio telescope. So that's a little crash course in interstellar chemistry, but we also have chemistry and even more complex chemistry in things like comets and meteorites in our own solar system. So in comets and meteorites, we see things like amino acids and other prebiotic molecules, and trying to understand how the chemistry that's relatively simple in interstellar space connects to these other objects is an ongoing challenge and something that astrochemists are trying to solve. And my particular interest is studying how ice chemistry affects the chemistry that we see in the solar system. And that's because ice is everywhere in interstellar space. I talked about molecules being frozen out onto dust grains, and that catalyzes reactions. But ice is also prevalent throughout the Milky Way. So you have ices on planets, except for Venus. That's the only planet that doesn't have any ice. You have it on moons, you have it on comets, asteroids. So ice really is everywhere and can shape the chemistry of our solar system. So ices start out simple. They're things like water, carbon monoxide, carbon dioxide. So this is another jargon for astrochemistry, is that when we say ice, we just mean any volatile that's in the solid state. So things like carbon monoxide and CO2 are considered ices in my field. We also have methane and ammonia. And these ices are processed by different things like gas collisions, UV photons, cosmic rays, which are just highly energized particles, thermal energy, and all of these things come in and irradiate the ice, break the different molecules apart, and then they recombine to form new molecules. And then those new molecules can go off into the gas phase. They desorb by different processes. And all of these processes can be simulated and studied in the lab. And the lab where I'm studying these processes, specifically the thermal energy, the UV, photons, and the desorption, is at NASA in the Sublime Lab, or the sublimation of laboratory ices millimeter submillimeter experiment. So this is a picture of Sublime. Usually the room's brighter, but for pictures, we like to turn the lights off in the lab because you can see this beautiful purple lamp. And I'll talk a little bit about what an experiment looks like. So we'll walk through that now. So here's the same picture. The thing that's covered in tinfoil is an ultra high vacuum chamber. So we're trying to get as much of the atmosphere out as possible to simulate interstellar or interplanetary conditions, but also so we don't have contamination. So we use ultra high vacuum chamber. It's a stainless steel chamber, and off to the left, kind of in the center of the picture, is what's called a cryostat. So that's just, if you think thermostat, but for cryogenic or really cold temperatures, that's what that is. And that can get our chamber down to about 9 Kelvin. So we're talking, again, the negative 440 degrees Fahrenheit range. So at the end of that cryostat is the sample holder. It's a gold-plated, about 1-inch piece of metal, and we can deposit ices on it. So when I start an experiment, first thing I do is I deposit some vapor at 10 Kelvin, and that vapor contains whatever molecules I want to be in my starting ice. So it might be methanol, it might be CO and water, it can be whatever I want. So I deposit my ice, I make my ice, and then I irradiate it using the UV lamp. So I usually do that for about an hour at 10 Kelvin, but I can do this at any temperature I want. That, if I'm thinking about maybe Pluto ices, I might use 40 Kelvin, for example. So what I can simulate whatever environment I want. And I have a video that hopefully works, so I can show you. Yeah, okay. This is like my favorite part of my job. So what's happening there is I'm flowing hydrogen through this glass tube. It's being irradiated by microwaves, like same thing that could be in your kitchen. And then I zap it with a Tesla coil, and you can even hear like the zap noise. And there's like this little thing of lightning that comes out. And then it glows purple. And I just think that's so cool. I get so excited when I get to use this lamp. But when it's glowing purple, it's emitting what's called Lyman alpha emission. And this is just a fancy way to say a certain type of UV light. That's the same kind of UV that dominates the solar and other stellar spectra. So we're really able to, with the vapor deposition, make a mini comet in the lab and then give it a sunburn with the lamp. So that's what I'm doing. So after we give our sample a sunburn, we warm up to 300 Kelvin. We have a valve that we can close, and we trap the sublimated gas in our chamber. And once we're sitting at 300 Kelvin, which is room temperature, we can measure the gas composition with submillimeter spectroscopy. And our detector is the red cylinder in the back of the experiment. So that is quick crash course in what my experiment looks like, but these experiments take a very long time, but that's what it would look like if I could do it in 5 minutes. So the reason why we use the rotational spectroscopy, and this is what really sets our lab apart, we're the only lab, we're the first lab to do this, and the only lab that's currently operating at the frequency or wavelength range that we use, is it complements IR spectroscopy. So traditionally, cosmic ice experiments use IR spectroscopy, which is looking at the vibrations of molecules that are either in the solid state in the ice, or they could be in the gas phase. But rotational spectroscopy is looking at the free rotations of molecules, so they have to be in the gas phase. And why we use rotational spectroscopy is because it gives us a different look at the chemistry. So we get unique molecular signatures. And what I mean by that is when you're using IR spectroscopy, you're looking at the vibrations of different functional groups. So if two molecules have, for example, a CO stretch, their IR spectral features are going to overlap. However, if we use rotational spectroscopy, every molecule that has a permanent dipole moment, has its own unique rotational spectrum. So that means that we can get an individual barcode for each molecule. So we can differentiate between molecules that might not be distinguishable in the IR. It's also ALMA analogous. So I showed a picture of that. It's called an interferometer, but that telescope that's made up of a bunch of different antennas. So we can directly compare our spectra to telescopes like ALMA because we cover the same frequency range as radio telescopes. So this is the same technique that's used by astronomers studying interstellar space. And then finally, it's structure specific. So we can look at conformers and isomers of different molecules. So again, these are things that can't be done in the IR, so we get a different complementary view using rotational spectroscopy. So I'm going to give an example of some of the first science that came out of Sublime. And this was not done by me. This is before I joined the lab. This was done by my lab mate, Katerina Yoakum, who is also a postdoc, an NPP, but she built the experiment while she was a graduate student. And one of her experiments looked at pure methanol ice photolysis. And the reason why she looked at methanol is because it's relevant to interstellar and cometary ices. Methanol is thought to be kind of the center of more complex organic chemistry, at least for oxygen-bearing species. And what this experiment has been done many times, just not with the rotational spectroscopy. But when Katerina did this work, these are all the different molecules that she found. And for the most part, they're not important, or for the context of what I'm trying to demonstrate. But what's really important are these three on the right: the ethylene oxide, vinyl alcohol, and ketene. So these are molecules that had never been detected in a cosmic ice experiment. In the case of ethylene oxide and vinyl alcohol, these are isomers of, I believe, acetaldehyde. So in the IR, they were invisible, and in mass spectrometry, they were invisible. So it wasn't until Katerina added rotational spectroscopy to the mix that you could see molecules that were invisible in other techniques. So I think that's really cool, and that just demonstrates the power of rotational spectroscopy. Next, I'm going to show you telescope data. So just here, what the spectra are showing you isn't actually important, but this just shows Herschel data, which is a space-based telescope, in red, and our experimental data in blue. And I'm just showing that you can directly compare both spectra. So I think that's something that's pretty cool about the technique that we use. Now I'll talk a little bit briefly about a project that I'm leading, and I won't say too much about it because this has just started, but I'm looking at ammoniated salts. And the motivation for the project is that there's this missing nitrogen problem on Earth and other rocky inner planets, but also in comets. There isn't as much nitrogen chemistry as expected. So this is a comet called 67P, and if you have heard of it, it's probably because of the Rosetta mission, which is a European Space Agency mission that went and visited this comet. And there's some data from this mission, from the Rosetta mission, that suggests that maybe some of the nitrogen is in salts, and salts are just specifically in ammoniated salts. And these salts are difficult to detect for a couple of reasons, including the fact that when they're in the solid state, they have features that overlap in the infrared with other things. And when salts sublimate and go into the gas phase, they immediately fall apart. So they're hard to observe. But if there are salts, they look something like this. So you have ammonium cyanide, ammonium cyanate, and a bunch of other salts. But I'm studying these two salts in particular. And the question I'm trying to answer is, if these ammoniated salts are indeed present, to what chemical pathways do they contribute in comets? So it's really exciting work because we have this hypothesis that there's these salts out there, but we don't yet know what chemistry they would facilitate. And so that's something that I'm trying to test in the lab. It's also exciting in a scary way because I'm mixing ammonia and hydrogen cyanide in the lab, and those are nasty things. So there's always, it's a bit scary too, but it's enjoyable. So hopefully I'll have some cool results in the not too distant future, and you might hear about those. So that's what I do at NASA, and I'm just going to end by sharing some perspectives. that I've gained. So some of these I've already said, but really try things that interest you, even if you don't think you are qualified. I think everything I've applied to, I have not thought I was qualified to do. And on paper, I really wasn't qualified. Like if you read the calls for things, for example, the position that I'm in now, I hadn't been in a lab for 5 years and I almost didn't apply. But my astronomy perspective from grad school was seen as a strength. So you might have unique skills, even if they aren't listed on the piece of paper on the web page. So if something interests you, just try it. If you get rejected from something, you're no worse off than you were before, besides, a little bit of a hit to the ego. Um, Connecting with people is crucial. I gave several examples of networking, but especially the one where I wouldn't have gotten to work at Harvard if I hadn't networked. So really connect with people and learn about different fields, because there's a lot out there that you might not be aware of, and having colleagues is really important. But also having friends is fun too. Everyone has their own path, and this is something that I often forget. It's tough. Like there's quite a few times where I'll compare what I am doing, especially my publication record, to my peers, and I'll be really disappointed, and I'll feel like, oh, I'm never going to get a job. But just try to keep in mind that everyone has their own path, and there's no right path. You're probably doing fine, and everyone has their unique strengths and also their unique weaknesses. But also, it's never too late to change direction. I never thought that after I didn't do any experiments in graduate school, I never thought that I'd be doing experiments in a postdoc. So, it's never too late to change direction. And at the rate I'm going, I just keep changing back and forth. So I'll probably change direction again eventually. And then chemistry really is the central science. It can help you be anything, even an astronomer. So if there's something that you're interested in, and it might not even be being a scientist, if you're interested in communication or art or whatever, I'm sure that there's a way that chemistry can help you. So a couple of shameless plugs before we open it up to Q&A. But first, I wrote an illustrated astrochemistry for the ACS in Focus series. So if you're at a university, ask your librarian if they have access to this collection. All the collections are also available on Google Play. And this is a really cool series because all of the books are led by early career researchers who are it feels weird to say, but experts in their field. And you can learn about different topics in chemistry that aren't part of the standard chemistry curriculum. So that's, a resource, that whole series, but also if you're interested in astrochemistry, definitely check out my volume. And then finally, I have a website, theskyisnotthelimit.org, and I like to post advice on my blog, The Professional Student, about applying to things like Fulbright, NSF Graduate Research Fellowship Program, and the CAS Future Leaders. So I have example essays and some tips on there, and I get feedback that it's useful. So hopefully, if you're applying to any of these things, they're useful for you. But for those of you who are graduate students and postdocs, and I'm not just saying this because I know Peter Carlton's on the call, but definitely apply for the CAS Future Leaders Program. It's really an amazing program for younger chemists. So with that, I will stop recording and thank you all for your attention.